In this video, I want to work through a couple of problems from the autonomous equations section. And actually, I'm going to do them all by hand rather than having them out typed out nicely. So I'm going to switch cameras and show you how to do these. So here's the two examples I want to do. Let's start with this one over here on the left. Y prime equals y times y minus 1 times y minus 2. Now the thing that I see right away on this is because I've already got it factored, that y equals 0, y equals 1, and y equals 2 are my equilibrium values. Those are, if you think of those as constant functions, they would definitely make the right-hand side equal to 0, and because they're constant functions, the derivative is also 0, and they would satisfy that equation. So when I'm drawing the slope field, what I know is that at y equals 0, the slope is always 0. When y is 1, the slope is always 0. And when y is 2, the slope is always 0. Now there's a matter of what's going on in between. And the way I see that is I draw the graph of y versus y prime. All right, so this is the y-axis and this is the y prime axis. And I'm just drawing a graph of this function. Well, this is a polynomial, cubic polynomial function. I know it's got a root at 0, 1, and 2. And it's cubic. When you multiply it out, the coefficient in front of the cube is positive, so it's headed uphill on this side. So it must look something like this, right? Cubic polynomial has two bends in it, as many as three intercepts. Okay, so now there's a lot of things I see. Oh, yes. The book also asks you, when you're doing the homework, to draw a phase line. And I don't do phase lines because I never use them. But here's what the phase line is. The phase line essentially is looking at the y-axis. I'm going to draw it this way, right? And you mark the spots where there are the equilibrium values, 0, 1, and 2. Those are the spots where the graph won't be going up or down. That would give you slope of 0. And then it's just a matter of in between what's going on. Well, I can see here when y is less than 0, y prime is less than 0. So that means things are headed downhill. So we put little arrows pointing down on this part. Likewise then, between 0 and 1, I see that y prime is positive. Remember, the heights here are telling you the slope of the solution. So the slope of the solution is positive between 0 and 1. So I got little arrows pointing upward here. And then between 1 and 2, the slope is negative. The y primes are negative, so the slope is negative. So I got arrows pointing down here and then positive up there. Okay. What we see here is, for instance, that 0, although we said it's an equilibrium value, things seem to be moving away from 0. So 0 would be an unstable equilibrium value. And 1 has everything pointed towards it, right? When you're above, it's going down. When you're below, you're going up. So this is a stable equilibrium value. And likewise, 2 is like 0, where things are pointing away from it. So this is unstable. Now, actually, you can see the stability or instability just right here. That is passing through this point with an upward slope here. It means that when y is less than y prime is negative. So when you're below y equals 0, you're headed downhill. You're moving away from it. When you're above y equals 0, you got positive slope, you're still moving away from it. So this is indicating of moving away in both directions. We're headed downhill here through that point. When you're less than 1, the slope is positive, which means you're headed up towards 1. But when you're bigger than 1, the slope is negative, which means you're headed back down towards 1. So that is this thing. So I don't really use the phase line to get the information. I can see it here, or I can see it once I draw the slope field. Because the slope field here, looking at this, I can see when y is less than 0, the slopes are all negative, starting off just barely negative. So when you're just a little bit less than 0, you're only going downhill slightly. And then when you're further down, you're going downhill more steeply, and then even more steeply the further down you go, right? And because this doesn't depend on x, then once I know it in one place, I just draw it all the way across, more and more steep as y gets further from 0. Now, in between 0 and 1, we have positive slopes, starting off close to 0, getting bigger, and then coming back to 0 again. So these are just barely positive through here, just uphill a smidge, and then uphill a little more in the middle, and then not as much when you start getting back towards 1 here. Okay. Between 1 and 2, it's the other way around, right? Between 1 and 2, it starts off as 0, goes negative, and then comes back to 0 again. So negative, but just close to 0. Negative, a little further away from 0, right? Going downhill a little more steeply. I'm trying to make these all the same going across, and then getting closer back to 0 as you get close to 2 again. Above 2, things start off at 0 and then positive. So uphill just a little bit, uphill some more, uphill some more, right? So I can draw that slope field reasonably quickly by looking at that graph there. Notice the equilibrium values of 0, 1, and 2. And what I see is things are pushing away from 2, things are pushing away from 0, but things are collecting in towards 1, hence the stable at 1 and unstable at the other 2. Now solution curves are going to look like, you can see them down here. If your initial condition is somewhere down below, that the solution curve down there is going to look like that. Solution curves in between 0 and 1, if you had an initial condition in here somewhere, they're going to have horizontal asymptotes like that, and then they work their way up. They go over, right? If your initial condition was a little over here more, it might look like that. In between 1 and 2, they're headed downhill. Up above, if your initial condition is somewhere above y equals 2, then it looks like you're doing something like that. So that I can do by hand fairly easily. Let me switch back to the other camera and just show you a nicer picture. So here's y versus y prime, the cubic, and then the slope field with some solution curves drawn in. Now I have to admit that in order to draw these solution curves, I solved the differential equation as a separable equation, right? You can divide both sides, integrate, divide both sides by this thing, and then multiply by dt and integrate both sides. And then it's really kind of complicated. You got to do some partial fraction decomposition in order to do that integral, but not too hard to do. The thing that's harder to do is then solve for y, which I didn't. I just left it as t is a function of y and plotted curves that way rather than y as a function of t. So these are different values of the plus c that you might put in there to see the different solution curves, right? So headed downhill over here, up, but then leveling off, down and leveling off in between here, and then headed uphill up above. Okay? So depending on what your initial conditions are. Now let's go back and try that other one. All right, so on this one, the first thing I notice is that it's not completely factored, so let me factor it. Y squared, this can be y minus 1 times y plus 1. And so what I see here is I see that y equals 0, 1, and minus 1 are my my equilibrium points, because any function y equals 0 or y equals 1 or y equals minus 1 would satisfy that equation. And then I want to draw a graph of y prime versus y. So here we go. This is y, this is y prime. I have a double root at 0, and I have single roots at 1 and minus 1. This is a 4th degree polynomial, which is headed uphill here. So it must do this and just bounce off of 0, head back down again, like that. So my phase line, my 0, 1, and -1, it's positive for y is less than -1, so this is all headed uphill here. It's negative in between here, so headed downhill. Negative here, headed downhill, and then y prime is positive up here, so it's headed uphill. So what I see here is I see an unstable equilibrium at 1, unstable. At -1, it looks like it's stable. You're headed uphill towards it, you're headed downhill towards it. So -1 is stable. And 0 is neither stable nor unstable. So above, it seems that you're heading down to 0 from above, but you're heading away from 0 down below. So this is neither stable nor unstable. It's sometimes called semi-stable. Drawing the slope field. Drawing the slope field at 0, got horizontals. At 1, I got horizontals. At -1, I've got horizontals. In between -1 and 0, I'm headed downhill, headed more downhill, not so much downhill, and still downhill here, right? More downhill, not as much downhill, and positives above and below. So going uphill here, more uphill, and going downhill. No. Uphill, sorry. These are going up, 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 up. And so my solution curves down below would be coming up like this, leveling off at -1. In between 0 and -1, they're going like that. In between 0 and 1, they're going down like that. And then up above like this. So you can see these 0 being semi-stable. If you're starting above 0, it'll eventually come down to 0, but if you start just a little below 0, you eventually pull away from 0. So this is stable from above, not stable from below. I actually think of this as, you ever gone hiking in the Grand Canyon? The trails look like this. You got, a mountain on one side of you, or the canyon wall on one side of you. You got the trail that you're walking on, and then you got nothing. You got just air and vast depths below. So you're walking along this trail, and if you were to fall this way, that's no big deal. You just bump into the wall and stand back up again. But if you're to fall that way, oh my goodness, it's catastrophic. You just keep falling and oh no. Yeah, that's my experience in the Grand Canyon. Actually, even though I know everything about physics tells me that gravity pulls downward, and even more so, gravity probably is slightly pulling this way because I've got so much mass over here. But it just feels like gravity is pulling straight sideways, and yeah. Anyway, where are we? Yeah, there it is. In order to draw this picture, I haven't solved the equation. I haven't actually integrated both sides and everything, but I get a real good idea of what solution curves look like just by doing this analysis. So here's a prettier view of that last example. Y prime versus y is this fourth degree polynomial graph. Um, and then we have down here the slope field with various solution curves. I may do one of these, actually show you how I solved these equations. I'll have to do that in another video, but you can see here that we have a stable equilibrium value at -1. All of these things are zooming in towards it. We have a semi-stable one at 0, where it's stable from above but unstable from below. And then we have an unstable equilibrium value here up at 1, where things are just moving away from it. Okay, so there you go. There's a couple of examples.